As the screen says, this is the 10th recorded lecture. That would include information from lecture exam 1 and this, lecture exam 2, which is addressing the respiratory system. This is the 4th lecture, recorded lecture, on the respiratory system. It's a snow day. I'm here in my living room. I've got a big load of oak firewood that was delivered last week. Snow is still coming down. It's Thursday, February 3rd. And so I sit by the fire with Lucy snoring away and Zoe very quietly sleeping off to my left as we explore more about how we breathe. Chapter 22, Lecture 4. I hope you're looking at the screen. Breathing is something that's automatic most of the time. As you adjust your breathing because you've been active, or as your breathing subsides because you've made it to your destination and now you're sitting. Perhaps you've been hurrying and jumping into a vehicle and now you've settled into drive. You'll notice, if you notice, your breathing and the rate of breathing and the depth of breathing will all change. Today, what we want to do is take a look at how that's controlled. But the good news is you don't have to put this on your calendar to remember to breathe. So I'm just curious, when you're just sitting there right now, you probably aren't counting, but now that we draw attention to breathing, it's one of those weird things where it always bugs me a little bit. I concentrate on breathing. I listen to myself breathe, and I just want it to go back to automatic. And I'm like, oh, but what if it doesn't go back to automatic right away and I need to concentrate and I forget? Am I going to just die? No, you won't. But you can go on and do other things and the automatic breathing will take over. If you're sitting down somewhere and you're rested, you're not, for some reason, really active, chances are you're going to breathe about one breath for about every 4 heartbeats. Yeah. So, if you had 60 heartbeats in a minute, well, then you'd expect divided by 12 would be about every 5 seconds you take a breath, and that's about 12 breaths per minute. It varies. This detailed physiology that I'm talking about today is well explained in Chapter 22. These actually may be the pages from the 7th edition, now that I think about it, but it's going to be in Chapter 22. And of course, you're responsible for the details in the text. Again, in Lecture Exam 2, there's only one full chapter on the test that I'm lecturing about, and there is another one that's a self-study. So I'm going to go over things rather generally. I like to do that to paint the bigger, broader picture, and then you can jump into some additional details when you read the text. Here's a few basics. Something quite interesting, in fact. Unlike in the heart, where there's an autorhythmic, so what is autorhythmic? What does the auto mean? Does it mean it has steering wheel and 4 wheels? No, it does not. What it means is it's something that is going to occur without us thinking about it, okay? That's what it means to be auto. Well, there's not that occurring for the respiratory system. Isn't that interesting? There is for the heart. The exact mechanism, as it says on the screen, is actually unknown of what's and how it's all controlled. But we're going to talk about some of the control here. So what has to happen? Well, the muscles that are largely helping to control breathing are skeletal muscles. And so these need direct stimulation from the spinal cord. And as it says, this innervation coming from the brain, and we're going to learn about it from the pons and medulla oblongata. So the rear or hind brain is controlling breathing. They send signals down with axons that then make their way down to the chest musculature and the diaphragm. If those nerves are severed by perhaps some horrible accident, well, then you won't be able to control breathing, and you would probably die without some emergency medical assistance. So skeletal muscles involved in require the nervous stimulation, and there are all sorts of different respiratory muscles that have to be coordinated. So here are the two brain regions I just mentioned, medulla oblongata and the pons. And within the medulla oblongata and the pons are clusters of neurons. And so these are groups. That's what they mean by group. Okay. And you can see that the VRG, the ventral respiratory group, produces a respiratory rhythm of about 12 breaths a minute, which is what I mentioned to you, which is then every 5 seconds, which, depending on your heartbeat, you could have a heartbeat of 60 to 70 beats per minute, could be a little faster. People who are in really good physical shape might have less than 60. So you can see that these three respiratory groups of neurons, clusters of neurons, have different kinds of effects. The VRG, ventral respiratory group, is producing this basic kind of background breathing. Then the dorsal respiratory group is allowing you to change the rate and the depth, right? So that you can change breathing in two significant ways. You can breathe more rapidly, you can take more breaths per minute, but you also can take deeper breaths or more shallow breaths. The same thing is true, and we're going to see in the heart. The heart can beat faster, and you may not know that the heart can regulate how much blood is moved with every heartbeat. So the volume that the heart is pumping out and the volume of the lungs each are variable, as well as the rate of heartbeats and the rates of breaths. Notice in the dorsal respiratory group, there's external sources that are having input, and we're going to talk a little bit about that later on. Then the pontine respiratory group, as you can see, is helping to regulate respiration in light of all the things that we do: sleep, exercise, speaking, and just some kind of emotional reaction. Here's where those respiratory groups are, and this is a rather small image on the screen right now, so please find this in the textbook. Again, this may be the 7E figure number. I'm sorry I didn't change these, but it'll be really close to this. And in the boxes right here, what really matters are these three respiratory groups we just discussed: the ventral respiratory group, the dorsal respiratory group, and the pontine. And here in the pons, you can see the pontine respiratory group, which again is a cluster of neurons. And then here is a cluster of neurons in the medulla oblongata. And they're sending axons down that are innervating, as you can see, the diaphragm and some chest musculature. So this is direct neural control of breathing. These are just some really nice figures highlighting these two brain regions. So here's the pons, where one of those, the pontine respiratory group, is located, and the other two respiratory groups located here. Breathing is a really fundamental thing that we have done since our ancestors first moved up onto land. And so we often think of the hindbrain, so those derive from the metencephalon and myelencephalon. We think of those brain regions as being very ancient or primitive, and certainly breathing would fall into such a category. So here's the kind of things that can occur as an output, how we can change respiration. First of all, I mentioned before, and you'd have to go back and look at, but I said that the regular respiratory rate can be impacted by certain parameters in the environment. And one is measuring the pH of cerebrospinal fluid. Cerebrospinal fluid, we talked about this fluid around the brain and inside the ventricles of the brain, central nervous system. We talked about this fluid in Human Anat Phys 1, right near the end of the semester. There are also chemoreceptors in these little knots, that is kind of thick areas in the circulatory system, referred to as the carotid and aortic bodies. And we're going to see in just a second. And the carotid and aortic bodies are measuring then certain chemistry of the blood and regulating respiration as well. What do they measure? Oxygen concentrations, CO2 concentrations, and pH, which is going to be influenced, by the way, by the amount of CO2 and O2 dissolved in the blood. And so here, again, probably a 7E figure, but really close, are those two thickened areas in our circulatory system. So you might not have gotten to the circulatory system yet, but these are really, really common carotid arteries, major arteries you're going to find in the cat. And in the cat, you'll find these coming up in the neck, the trachea, and behind it, the esophagus will be running right in here. This will be clustered, by the way, into the mediastinum. And here we've got those vagus nerves. And that's the ones that we're talking about controlling respiration on the diaphragm. In any case, these are the thickened bodies, part of the circ system, that are helping sense then oxygen concentrations, CO2 concentrations, and measure pH. A third feedback mechanism for respiration are stretch receptors in smooth muscle. And so as you take a bigger and deeper breath into your bronchi and bronchioles, then they're sending signals. These stretch receptors are, oh my goodness, you're taking a great big breath, and there's feedback there saying, okay, things are stretching, we're taking in more air. Or the reverse, the smooth muscle might be constricting. So there's good feedback there. If you can hear a new sound in the background, it sounds like someone's plowing the roads. I hope. Finally, and this is really important, as I clear my throat a little bit, maybe because I got a little smoke here, I'm going to adjust my respiration because I may have had, some dust or some smoke from the fireplace. And I'm adjusting my respiration. I'm going to clear my throat a little bit from excess mucus, and I'm going to then help hopefully expel that extra mucus, or cough, and possibly even sneeze would be part of this. So these are, again, adjustments. These are 4. You can go back and find the first 2. Ways that our respiratory system receives input, such as irritants, right here, number 4, and responds our respiratory rate. So here's another related question. Well, what if you are breathing too fast? What if you're hyperventilating? If something triggers that? And maybe this has happened to you. Maybe you've seen it happen to others where they're breathing too fast. Well, I'm glad you asked. In hyperventilation, you have some kind of anxiety, something that's triggered your breathing. And here's the bottom line. Your breathing rate is so rapid that you're getting rid of more CO2 from the body than it's produced. Yeah, you're actually depleting the CO2 levels. So what's going to happen? As blood CO2 levels drop, the pH rises to a more basic pH. Cerebral arteries are going to constrict, restricting that kind of blood, making its way to the brain. When we have less blood going to the brain, guys, you're likely to be dizzy or possibly even faint. So lightheadedness might occur. And what can you do? Well, you can change that rate if possible and slow down. But if that's not possible because of the anxiety or whatever's going on, breathing into a paper bag helps because, well, think about it. As you breathe out into the paper bag, that's your breath. And then you breathe in what you just breathed out. And so you are not really dropping the CO2 level very much by breathing out. You don't want to keep doing this, but it'll stop the problems and you'll feel less lightheaded. So breathing into a paper bag can help with hyperventilation. Well, what about people who choose to hold their breath? like perhaps, and I think this is falsely colored. I sure hope that they didn't take a picture of a kid and told him to hold his breath. And by the way, if his face is kind of purple, I'm thinking his arm should be a little purple here too. So I'm thinking they've colored in his face. In your textbook, they note about a kid holding his breath. And they said there's limits to voluntary control. And little kids can threaten to hold their breath until they die if they don't get their way. What I did, my kids really, we just explained these things to them quickly, and maybe that's a sign of just how smart my kids are. They both have their doctorates, one in occupational therapy and one in chemistry. In any case, they didn't hold their breath a long time, but I would have just made sure that the area around them was a nice soft area, like a sofa or something like that, or cushions, or on their bed, and then tell them to knock yourself out. Like, literally knock yourself out, holding your breath to the breaking point. And you could pass out by doing this, but as soon as you pass out, then what's going to happen is automatic, as it says, automatic controls take over, and you start breathing again. Now, what I'm not going to talk about, but I'm fascinated about, and you might want to go look it up on your own, are people that deep dive and hold their breath for very long periods of time, sometimes over 4 minutes. So if you want to have some fun and do this while you're sitting down, and make sure that if you somehow passed out, you wouldn't hit your head. But see how long you can hold your breath. And by the way, notice that when you've gone a long time, and maybe you can hold it for a minute, that as soon as you stop holding your breath, you're going to breathe rapidly to try to get rid of that extra CO2. In any case, I don't know if you've ever talked to someone who's practiced at holding their breath, but I had a chance to stay at a person's house who does this. They were a bed and breakfast when my wife and I were in the southern island of New Zealand. And so down at breakfast, he was telling us about things he did and told us about this, and I pursued it a little bit. I told him about my background a little and that I'd like to learn more about this. And he was talking about all the preparation of the really deep breathing and exhaling, and what they were able to really feel like they really oxygenated themselves before they went under. And then he was talking about the mental control, which is exactly what this is talking about. The mental control of suppressing the automatic urge to start breathing. And he said that's what you really work at, is suppressing this reflex. And that just doesn't sound like a good idea to me. I like my reflexes, especially the ones that make me breathe and make my heart beat. Okay. But nonetheless, apparently some people think that this is enjoyable. So what are we doing when we're breathing in and exhaling? We're expanding the chest cavity, and air is coming in through our, well, probably nose or mouth. And this is negative pressure. And then positive pressure here where we're exhaling, and that forces the air out the nose. Let's talk about that. Why does air move in and out of the lungs? Well, we said positive and negative pressure, but let's really explore that. Let's make sure you fully understand this. Now, also know that students of mine have gone on into respiratory therapy, or a person who's supporting people with respiratory problems. And this kind of understanding is fundamental to their job. Or if you go into nursing, you might be helping people out with respiratory problems. And it's best, I think, to help people because you understand the mechanisms. You understand what it is that you're doing or the equipment is doing or others are doing, so that you know it's not just a matter of duties and tasks, but you really understand what are we trying to accomplish. Okay? So do you have to learn a few principles of physics? Yep. Atmospheric pressure. So I know you think about this, but the air that's above us is pushing down on us. And that pressure is all around us, or all around our body, and it drives respiration. Here's what atmospheric pressure is at sea level, and that's 1 atmosphere in our standards. I think you know that when you go up to higher elevations, so I have family that lives at 7,000 feet. When I go up to visit my aunt at 7,000 feet, the atmospheric pressure is lower and the concentration of oxygen is less. So I breathe more rapidly, especially in the first few days when I get there. And we'll talk about those other kinds of accommodations, like an increase in the production of red blood cells when you go to lower oxygen areas. Well, here's a principle of physics we need to consider. Boyle's law. It's simply that pressure and volume are inversely related. Okay? If you take a given amount of gas and you increase the volume, the pressure will drop. Take that same gas and you squeeze it more, and the pressure will go up. Okay? So if there's a set volume of air in the lungs, and then you expand the lungs, the pressure will drop. That's the intrapulmonary pressure. And make sure you know basic word roots. You should have learned intra a long time ago. Intramurals is where we compete against ourselves in sports, usually within the college. Intercollegiate athletics, we're competing against other colleges or universities. So intra is within. So the pressure within the lungs falls as the lungs expand. And if the pressure falls below atmospheric pressure, well, then air is going to move into the lungs. Okay? So it's a negative pressure. It's a pressure below atmosphere. And so air is from atmospheric pressure is going to be driven into the lungs. Likewise, the reverse is going to happen, guys. So if you now compress the lungs and decrease the volume, the pressure inside the lungs, the intrapulmonary pressure, rises, and you will exhale. And air will move out of your lungs. How do we measure these kinds of pressures and forces? Well, physiologists, respiratory physiologists, use a measurement of centimeters of water, that is, centimeters of water moving up or down. And you got a column of water, so if you're generating a pressure, how many centimeters of water are you driving up in a column? And interestingly, you got to think about this. This is actually the water system is more sensitive than mercury. And why? Because mercury is a heavier or more dense liquid. And that means that where you'd have 1 millimeter of mercury, you have about 1.4 centimeters of water. So what's the difference here in distance? 1 millimeter, 1.4 centimeters, well, that's 14 millimeters. That means there's 14 units for water compared to 1 unit for mercury. So as you're measuring these little bitty things on some scale bar, you can more precisely read the scale when it's units that are 1.4 centimeters instead of 1 millimeter. Okay? 14 millimeters here, 1 millimeter here. All right, now this is kind of complicated. So you really got to bear with me here, and maybe this is a pausing point if you're in the middle of something or you need to take a break. But you want to come back to this, and this is important. Intrapleural pressure. What this is we're talking about the space between the two pleural membranes, right? So there's the pleural membrane covering the lungs and the membrane lining the thoracic cavity. Okay? Between these two pleural layers, when the chest expands, why do the lungs expand? And in short, that pressure lining the chest, that layer, is wet, and it somewhat sticks or adheres to the surface of the lungs. So when the chest expands, it pulls that lung tissue with it and expands it. Now, as you're pulling and stretching the lung tissue, it wants to snap back. But meanwhile, the chest, or diaphragm, is expanding and pulling in the opposite direction. So the lung tissue wants to contract, wants to pull away. It's been stretched and wants to snap back like a rubber band. But the chest is pulling away. And so what that's going to do is there may be a very, very small space that's between the parietal and visceral pleura. Okay? So, parietal and visceral pleura. What were those? Well, the parietal is the one that's lining the thoracic cavity. The visceral pleura is the one that's covering the lungs. Okay? And there's a watery fluid between these, and so they're sticky. So as the chest expands, it's pulling that surface of the lungs outward, and that's expanding the lungs. Okay? And you can see it's a negative pressure that's in between these two pleural membranes. Again, pleural here is for lungs. So the two layers, the visceral and parietal pleura, cling together. Ribs swing upward and outward. Visceral pleura clings to the parietal pleura. Because of the cohesion of water, it pulls those lungs open. And what happens when you pull the lungs open? It stretches the alveoli. And we've just talked about those a couple lectures ago. So the entire lung is going to be expanding. And as it does, go back to those laws. As you expand the volume of the lungs, the pressure is going to drop in the lungs. And as the pressure drops below atmospheric pressure, air is pulled in. So they show this bucket. You can work through the bucket analogy. This is a figure in your book, but they're going through all of the details. And I'm not going to go through this figure, but I urge you right now to pause the lecture and to go look very, very closely at this particular figure. Okay? It's really helping to pull things together, and you can see the respiratory cycle right here. Now, this is another really, really interesting aspect, and I'll confess that until I started teaching Anat and Phys and Anat and Phys 2, I hadn't really thought through this aspect of respiration. So there's another law here related to physics called Charles' law, and that says that when you look at the volume of a gas, it's proportional to the temperature. So I don't think you're surprised to find out that when you heat up air, it expands. And when it expands, right, it's less dense. And so that's how a hot air balloon works. Somebody's using some kind of big blower, a big giant blower with flames. And they're heating up the air, and it's trapped. That heated air is trapped in this balloon. And that air expanded has lower pressure. And it's lower pressure than the atmosphere, and so the balloon rises. But here's a different aspect of this. Think about on a cold day, just like we got right now. That's why I got this lovely fire going as I'm lecturing to you. On a very cold day, and it's not 16 C right now. It's C. Yeah, it might be -5 right now. Yeah, -5 would be 23 degrees Fahrenheit. I think it's actually cooler than that. So it's below freezing. It is freezing outside right now. So if I go outside, I breathe in some of that really cold air. And as that air enters into my respiratory tract, take a look. Inhaled air is warmed to about 37 C, which is about 99 degrees Fahrenheit. And by the time it reaches the alveoli, it gets warmed up almost this much. Well, you just warmed up the air you inhaled. And so what's going to happen? That inhaled volume, in this case, they're given an example of 500 mLs, and under these temperature differences, which is not all that much, okay? So they're just saying 60 degree Fahrenheit outside, that's maybe May or June weather, and they're going to heat it up from 16 to 21 C. It's going to expand from 500 to 536. And here's the cool part. As you inhale cold air and it's warmed in your respiratory tract, the warming process, as that air travels deeper and deeper into your respiratory system, it expands. And as it expands, it's filling up those alveoli and stretching them. Isn't that neat? Okay, what's quiet breathing? Quiet breathing is what we do when we're not really thinking about it and we're not active, so we're just sitting around. That might be what you're doing right now. And up until the fact that I brought this up again, you might have been breathing just fine and not giving it much notice. Okay? Well, in quiet breathing, as you can see, there's not a lot of movement in your chest. It's only enough to change the volume by about a half a liter, which is not much. That's less than a soda can. I'm trying to think of the volume of a soda can. So I'm going to look at my water bottle right now. Yeah, it's half a liter is about 17 ounces. So about a third of. Yeah. So if you have a soda can around you, I'm going to guess the volume of soda cans close to 300 mLs. So this is a little more. Wait a minute, let me try this. Maybe this works. Oh, there you go. Sorry, I can do it this way instead. So when you have a half liter bottle, which is the typical bottles of water, so I got one here. You can hear the crunchiness. We refill our bottles at home. We don't throw these bottles away. We just continue to use them. It's the best recycling. We just don't buy another one. And I have really nice filtered water in my home, and I fill them up with. Okay, so that's a one of those half liter bottles like what you buy of water. In any case, that's not a lot of air moving. Largely, when you're doing this quiet breathing or relaxed breathing, it's a rather passive process. As you can see, when you breathe in just a little bit, you're stretching things, and then as you breathe out, it's the passive process mentioning here is simply the recoil of the thoracic cage. That's both the connective tissues and the muscle, also the bones. And so the recoil is going to compress the lungs just a little bit. Of course, as the lungs compress, the thoracic cavity decreases. It raises the pressure inside the lungs, and the air flows out. Forced breathing. In this case, this is where you're really working at it. Okay, maybe you're inflating a balloon. For me, I was blowing a little bit before on my fire to get it going and to have the flames come up in just the places that I wanted the flames to come up. In that case, I'm going to use an awful lot of these extra muscles, the extra muscles of the chest, and you're going to generate that intrapulmonary pressure, making it very high and forcing even more air out. Other related topics. What's a collapsed lung? So as we're considering these mechanisms, what's a collapsed lung? Well, this is called a pneumothorax. That means literally pneum is lungs, lung cavity. It's the air in the chest is really what it's saying, and it's implying that air is not in your lungs. So it's air in that pleural cavity space. Okay? So we had the visceral pleura over the lungs and the parietal pleura lining the chest cavity. And we said that there was a fluid there between the two. And as the chest expands, that adhesion between those two pleura pulls the lungs open. Well, not if there's air in there. You can expand the chest and your lungs don't do much. Okay. So what could cause this? Well, some kind of very serious puncture of a thoracic wall. So auto accident or gunshot wound or stabbing. Okay. So what's going to happen when you breathe in? Air is literally going to be sucked in to this space. And so if the space becomes air-filled, then you don't have that negative pressure between those two pleura that allows the lungs to expand. And instead, what's going to happen is these lungs are going to collapse. The lungs are going to just recoil down, and you can't fill them. Okay? So that's a real serious problem, guys. And if you run around on an ambulance in some role of some sort, a paramedic or an EMT, you'll know all about this. And that, as Lucy starts whining more, she's upside down at this point, that ends a shorter lecture here, lecture 10. And I have a longer lecture that is coming after this, the 11th lecture, And that will be the last lecture